A fan wall is not simply a row of fans. It is one air-moving system built from multiple smaller fan modules. The useful question is not how many fans you can fit. It is how the array, the plenum, and the control sequence work together at the required duty point. Imagine replacing one large fan with a 3x3 array of direct drive plug fans. All 9 draw from a common inlet space and discharge into the same air handling section. Because the modules operate in parallel, their airflow contributions add at approximately the same pressure. 9 modules delivering 2,000 cubic meters per hour each would give 18,000 cubic meters per hour only at the pressure where each module can actually deliver that flow. That last condition matters. You cannot multiply one free air number by 9 and call it a selection. Build the array curve by adding module airflow at equal pressure, then intersect that curve with the resistance curve of the filters, coil, dampers, grills, and ductwork. The intersection is the installed operating point. Here is real Longwell fan wall hardware. The repeated cells make the architecture easy to see. Each module has its own impeller, motor, inlet geometry, electrical connection, and mounting position. The surrounding frame and plenum are also part of the system. Poor inlet clearance or recirculation between cells can move performance away from the catalog curve. One benefit of a well-designed array is airflow distribution. A single discharge can create a concentrated high-velocity region across a coil. A correctly spaced fan wall can divide the flow into smaller jets and produce a more even face velocity pattern. But uniformity is not automatic. Module spacing, distance to the coil, blanking plates, wall leakage, and the inlet condition must all be checked. Control can follow 2 common ideas. In all fan modulation, every available module runs together and changes speed with demand. In staged control, the controller starts or stops modules and adjusts the speed of those that remain active. The best sequence depends on module efficiency, the load profile, minimum stable speed, acoustics, and the required pressure. Energy savings are therefore a result to calculate, not a fixed percentage promised by the layout. Now stop the center module. The other 8 can continue moving air, which avoids the single point of failure of one large fan. But the available array curve changes immediately. If the controller speeds up the remaining modules, airflow may recover partly or fully only when motor power, current, sound, speed limits, and the system curve allow it. True N+1 redundancy means the specified duty point is verified with one module unavailable. It does not mean that any extra fan automatically guarantees full capacity. Modularity also changes service work. A technician may isolate and replace one smaller module while the remaining system follows an approved reduced capacity sequence. That can be valuable in data center CRH units, hospitals, large AHUs, commercial buildings, and retrofit projects where downtime and access are constrained. The safe procedure, isolation hardware, guards, and service clearance still have to be designed. Specify a fan wall as a system, total airflow and pressure at the same duty point, module model and quantity, normal and failure operating points, complete array curves, absorbed power, sound, controls and communication, electrical distribution, inlet and discharge clearances, airflow uniformity, leakage, service access, and the actual filter and coil losses. Then compare annual operating points, not only the peak efficiency number. The definition is simple: many fan modules, one engineered airflow system. For a project-specific array and failure case review, visit longwellfans.com.